in outline, what have we done? We talked about the transport theorem for many weeks just to get ourselves oriented about how to deal with changes of frames, and then talked about single particle dynamics, multi-particle dynamics. We got to this end where we talked about if you have a system of multiple particles or even a continuum, you could break down the dynamics into translational dynamics of the center of mass and also the rotational dynamics. And it was described by the two different equations. So this is sometimes called the Newton-Euler approach to modeling rigid bodies. The Newton approach gives the translational motion. If you remember from, I think it was lecture 9, we talked about something that looked like Newton's equation, F equals ma, for the motion of the center of mass. So the translational motion of the center of mass. So that means we've got an inertial frame, some kind of origin, and floating yam, arbitrary thing. But it is a rigid body, and we're tracking the location of the center of mass. So if this has a total force, we'll just write it that way. And this is the external force, that's total external force, because we don't even consider internal forces, like if it's magnetic or something, who cares? So we have a total force on the body. The Newton approach is just that F is equal to the total mass times two inertial derivatives of the position. Right. RC double dot is two inertial derivatives of the position. So this is sometimes called, we called it before the superparticle theorem. Some people have even called it Newton's law, but it's kind of derived from Newton's law. It looks exactly like Newton's law, but it's not exactly the same. Total external force over here. Some people have even gone so far as to call it Euler's first law, but that might confuse you. Just think of it as Newton's law, and if anybody asks for details, you could look them up. So this gives the dynamics of the center of mass. So if we're talking about spacecraft, maybe that the location of that center of mass is given with respect to the center of the Earth. So we're not saying anything about how it rotates. We're just saying how the center of mass moves. So the center of mass is moving, and it might also be rotating. And of course, our focus is on that rotational part. This was translational motion. The rotational motion also harkens back to lecture 9 when we talked about Euler's equation. This is the one usually reserved for the word Euler's equation. And sometimes people will weirdly call it Euler's second law. Just letting you know, you're going to hear a variety of terminology out there in the big bad world. So the rotational motion, let's draw the potato again. It's easier than other things. It can be drawn. So there it is. And it's got a center of mass. I guess we could label that up there and down here, which is a body fixed frame attached to this. So we write the frame as, B, and maybe we write the body as fancy B. And the main thing that we're going to care about here is the angular momentum. So here's the angular momentum. Typically, it's angular momentum with respect to the center of mass. B frame is attached to the body. And right now, we're not specifying if this is a principal axis frame. It's just a frame attached to the body. Then the governing equation, the equation of motion, is going to be, it's this just one derivative of, maybe I'll write it in analogy to what I have up there. It would be HC over dot equals LC, using the book's notation for what the moment is, the moment or the torque. So here is a torque. It's a torque vector about the center of mass, moment or torque. Of course, HC dot, this is just shorthand for a derivative with respect to the inertial frame of the angular momentum of the body about the center of mass. And sometimes this is called Euler's second law, but again, that's kind of weird and confusing. So we will just call it Euler's equation. This is Euler's equation. And we're going to write Euler's equation in a bunch of different ways. What is LC? The total moment, total external moment. And we could write a formula for it. I'll draw the shape again. I'll write the moment with respect to some reference point. It doesn't have to be the point C. So in general, how do we get the total moment? And about, because we might not always just want it about the center of mass, about some point P on the body. So here's a point P. Here is the center of mass, and here is a volume. So we're going to have to integrate. I'll write the location of this. This is the location of that volume element. This is the volume element dV. It's got a density in it. This might not be uniform density. dV with respect to the point P, the total moment with respect to the point P. This is defined to be integral over the body, so over the volume of the location of that volume with respect to the point P cross. And now it's like the force acting in that little box. I'll use a different color. Here's a force. This is little f. It's a force density, F dV. So it's at that location. This is a force density, which means force per unit mass. We're summing over all of the little mass elements, dm, which is rho dV. So I'll put rho dV. We're allowing for the fact that rho, the density, might be different throughout the body. If it's not, then you could pull it out as a constant. This is how you would write the moment about an arbitrary point, including the center of mass. For example, if we're in uniform gravity, like near the surface of the Earth, later we won't be in a situation where we would consider the gravity uniform. When we talk about gravity gradient satellites, they actually use the fact that gravity pulling at the point closer to the Earth is stronger than the point furthest. But for now, let's just assume uniform gravity. Uniform gravity means that the force density, this is the force per unit mass, that has units of acceleration. So this is the direction of the gravitational acceleration. So let's just calculate this. For uniform gravity, it is got a triple integral of the body r dv p cross product g rho dv. This will end up giving you location of the center of mass cross m G. So it looks like location of the center of mass. What's location of the center of mass? If I were to sketch it up here, this is the location of the center of mass with respect to our point P. So RC is the same as the vector from P to C. It's the location of C with respect to P cross the usual force due to gravity, mass times acceleration. So that's just an example. It might be different in different contexts. Okay, so we've got, if I were to highlight them again, I'll highlight this one. This is the one that we'll focus on. That's with respect to the center of mass. If you have an inertially fixed point, then another variation of Euler's equation would be the inertial derivative of the angular momentum with respect to that point P. Think of a pivot point equals the moment, total moment about P. So that's another variation. We could say more. You write it that way, but we usually write Euler's equation in a body fixed frame, which means we want to take the derivative with respect to a body fixed frame. So we now use the transport theorem. So the transport theorem would say take the derivative with respect to the body fixed frame plus, and now we're talking about one frame with respect to another frame. Here's the B frame and the N frame. They're just different triads of unit vectors. And what we have called angular velocity is actually the angular velocity of the B frame with respect to the N frame. So then this would be plus omega of the B frame with respect to the N frame, but that's just the angular velocity cross HP equals the total moment about that point. So that's just another way to write it. It uses the transport theorem. So if we use the center of mass as our reference point, we would have something that looks really similar. It's just with respect to the center of mass, omega. And omega is just the angular velocity of the body. I'll just give you those two. Right? They look the same except for that subscript. So this is also called Euler's equation. I think in the book, this is what, 432. It's also called Euler's equation. We're just writing things with respect to the body fixed frame. Why are we going to want to do that? We're doing that because later we'll write HC is the moment of inertia matrix. What do we calculate that in? Not the inertial frame. We usually calculate that in the body fixed frame because then we've calculated it once and for all. So that means we've got the angular momentum written in the body fixed frame, and it'll be the moment of inertia times the angular velocity written in the body fixed frame. So we're going to eventually use this. We're not going to use it quite yet. There's more I want to say at this level to kind of build some intuition. There is this qualitative analysis of spinning bodies that we can do just to get some intuitive feel for things. I think this is helpful. If you haven't seen it or thought about it, then this will provide at least some idea of what's going on. So we'll look at this first one that I wrote up here, because this is mostly useful, at least in the examples, if there's some kind of pivot point. So just copying what we have up there, writing the time rate of change of the angular momentum with respect to a body fixed frame plus angular velocity. Okay, here we go. If we have this, what's a good picture to have in mind? A spinning top or a gyroscope. This is a still from a video. Okay, so we got a gyroscope. For the gyroscope, there's the part that spins, or to kind of highlight it. There's this giant flywheel, and it's spinning. We don't yet know which way it's spinning, but it's spinning a lot, and it's attached to a frame. We will call this the body fixed frame. And that frame could be moving with respect to an inertial frame, which I'll just sort of put centered at this pivot point. I'll call that P. And then this is probably over here, the center of mass. The idea is if you have a gyroscope, there's a flywheel, kind of like your spinner, and it's spinning very rapidly with respect to the frame. So this flywheel spins rapidly with respect to this B frame that it's attached to. So we could say that it has a very large angular momentum that isn't changing much. That means over here, with respect to that body fixed frame, this is not going to change much. And HP is really large. The magnitude of HP is large. Let me actually show you a video of this getting spun up. Spinning. And the way that it's spun, the angular velocity is actually pointing up. If we were to watch it again, it's being spun. I guess the way that we're looking at it, it's counterclockwise. I'm going to place it on here. And it's spinning rapidly. It's going to have a fixed pivot point. What's it going to do? It's going to move in some direction. You've probably seen a gyroscope, right? It's going to set it down here. It's going to move either to the left or to the right. And you could figure that out using this qualitative argument. And that's all we're after now. Which way is this thing going to rotate? Which way is the frame going to rotate about that pivot? So he's got the flywheel spinning. It turns out the flywheel is spinning very rapidly in a particular direction. Let's first figure out what the moments are. So when you have this first part equaling roughly 0, then that means you're just left with this over here. So you could qualitatively figure out which way is the moment. The moment here, the moment about P for this situation is what? Moment about P is due to, the only force here is gravity. So from this point P to the point C, we've got that, which I think before I called that R, little r sub C, and then gravity pointing down. So the moment is, using the right-hand rule, R cross F. So it's actually pointing into the screen. We have to know which way the angular momentum is going. The angular momentum is actually going this way. It's hard to see from the video. So if it's spinning very rapidly, going that way, then what direction will the frame go? So if we know HP, that direction, and we know L, then we have to figure out what does omega need to be for omega cross H to equal L. And using the right-hand rule, omega needs to be pointing down. So omega, this is omega of the B frame with respect to the N frame. So if that's correct, then our prediction is this will be like coming at us, because following the right-hand rule, because of omega. If omega is pointing down, my thumb points down, my fingers curl in the direction that the whole frame is rotating. So let's see if that holds true. We'll watch the gyroscope get placed. Okay. Yeah. So this is omega pointing down. Omega pointing down means that your fingers are curling using your right hand, doing that. So this had the very high angular momentum. It's actually pointing towards the pivot. We could do another case just to see what's going on here. That pivot point, actually, it doesn't matter if it's on a stand. If you start with that thing not moving, it doesn't matter what it is. So this could be at the end of a string. So there's this other video. I think this one has sound. Got a bicycle wheel hanging from a rope. It's sort of like a giant version of the gyroscope. And he's getting this spinning pretty rapidly. You think of, okay, which way is he getting it spinning? He's getting it spinning so that right now the angular momentum is pointing down. And you'll be able to watch these. And then he's going to set it up sideways and let it go, and it's going to spin one way or the other. Let's try that over here. We'll just show another image. So this is spinning. We'll use some different colors that are a little bit easier to see, right? We still have gravity. Here's that point P. Here's the center of mass, RC, and then gravity's pointing down. So what's the moment? We know the moment here. It's R cross F, so it's coming out at us. So the moment R cross F is pointing towards us. The angular momentum is very large, but away from the pivot. So the only thing that's different, right? The moment is the moment. Angular momentum is pointing away from the pivot. So what does omega have to be? Does it point up or down? For this equation up here to be correct, we need that. So omega, if I do my right hand, omega needs to be pointing up. Omega cross H, pointing out of the screen. So it's kind of along here, omega of the bicycle frame, basically. So with that prediction, that means that the bicycle wheel should be turning in the opposite direction as this gyroscope, just because of how it was initially spun up. How do I draw this nicely? Kind of around that way. And then coming into the front, going behind there. So that's the prediction based on the qualitative analysis. Let's see if it bears out. Okay. And okay, good, it's going that way. And this is kind of remarkable because maybe like, how is that bottom of the rope not swinging like crazy? Yeah, as long as it starts out, forces it up so that that pivot point is initially not moving. And that's why this works. It is kind of amazing, I think. We could look at other situations where maybe we don't know the moment. We actually want to find out the moment. And that's related to the fidget spinner. If you've played with a fidget spinner long enough, you know that it moves in weird ways. If you hold it, you get it spinning, and then you kind of twist your wrist, you feel something that's not highly intuitive. So what about the fidget spinner? Fidget spinner. So here is a fidget spinner. And what we're imagining here is that you're going to rotate your wrist. You get this thing spinning. So if let's say I'm holding it and then I'm spinning it down. And I look kind of like what's pictured there. If I spin it down, then it's each little part of it's going this way. So what direction is the large angular momentum? The large angular momentum is here. I won't even put a little subscript. It's just a large angular momentum using the right-hand rule. Ugh, it's going that way. And now if I were to rotate my wrist, so maybe I'll move it this way. So if I've got the fidget spinner and I try to turn it, I can feel it resisting. And I have to exert some moment on it to make it not turn weird. So you rotate your wrist, and I don't know, maybe the pivot point is up here for your wrist. Let's say I'm rotating in the direction of the arrow. So that means I have an angular velocity. I'm imposing some angular velocity that's coming out of the screen, because according to the right-hand rule, if my wrist is rotating that way, then that's the angular velocity vector it's pointing out. So what is the moment that my wrist must impart to maintain this movement? Well, what do I have? I've got omega cross h, according to up here, must equal the moment that's applied. Omega cross h, the moment's pointing this way. So this is L is the moment my wrist must impart to maintain this movement. And you can feel it resisting that, and that's why your moment has to be what it is. As you rotate your wrist in the direction shown, what you'll feel is that this thing wants to kind of turn that way and the backside turn that way. And so you have to exert a moment that's in that direction to resist it. So you could try it out, try it at home. And you got this, and I could feel it wanting to do weird things, and I have to resist. Now, if this was spinning like crazy, it would break my wrist. I couldn't maintain the movement without breaking my wrist. That's why these only have a certain size, fun size, not dangerous break your wrist size. It's all fun and games when it's a fidget spinner, but what if it's landing gear? What if it's landing gear? So there's an analogy with landing gear. Some planes have had landing gear this way. I don't know if all planes have. Yeah, they don't actually do landing gear this way anymore. But old-timey landing gear. This is the wheel, right? The wheel, as it's spinning during takeoff, is going to be moving extremely rapidly. And if you try to turn this up, it's exactly like the fidget spinner. And you're going to have lots of moments imparted up there where things could break. So if I give you a sketch of landing gear, it's kind of aligned with sort of the same way that this fidget spinner. We've got the wheel rolling on the ground. All right, here's the ground, let's say. If this is rolling in the way shown by this arrow, then you have a really large moment. Here's at some later time. We've got a really large moment in that direction. And we're imposing by, let's say, some motors up here to make the landing gear turn up. And by the right-hand rule, that means that the angular velocity would be in this direction. And because of that, to maintain this movement, the moment that must be imparted it's going to be in this direction. Omega cross h. So if I have h very large or omega very large, right? L, I'm just going to rewrite what I have up there. It equals omega cross h. So if you retract very rapidly spinning landing gear and you retract it quickly, this moment could be so large that it does damage, right? If the magnitude is L is large enough, it means you're breaking stuff. This could break. The landing gear mechanisms could break. And that's definitely not what you want, especially on takeoff. How are you going to land? So most landing gear does not fold up this way anymore. It actually just gets pulled up. Then you don't have this kind of omega cross h moment showing up. If you don't worry, if you fly on commercial jets, most landing gear just retracts upward. It doesn't fold sideways, but you get the same. It's completely analogous to holding this fidget spinner and then trying to turn it up. And you can feel that it's an increased moment when you turn it rapidly versus slowly. So when they did do this, they probably tried to do it as slow as they can. Now we have a great intuitive understanding about three-dimensional rigid body dynamics. We'll revisit this later, but you might think about it or Try it out. If you don't have a fidget spinner, get some landing gear, I guess. We're going to get back to the quantitative. That was qualitative, just what are the directions of vectors. But now we're going to get quantitative again and talk about the rigid body dynamics. We're going to look at Euler's rotational equations of motion in more depth, just following on from what we have up there. And this is, if you're in the book, 4.2.3. So we've got this, and I'll be focusing on the moment about the center of mass, because that's what matters mostly on a spacecraft. The rotational dynamics with respect to the center of mass. So we've got this plus omega cross HC equals LC. And now we can substitute in what we know for the angular momentum written in the body fixed frame. It equals the moment of inertia matrix, which we have fussed about, times omega, so the angular velocity, again, written in the body fixed frame. So what this is, if you want, we could write it out, not particularly enlightening, but there it is. And this is all in body fixed frame. And then omega 1, omega 2, omega 3. Right? We're trying to make a connection with the angular velocity because the rigid body kinematics, all the Euler angles and how those change was related to the angular velocity in the body fixed frame. So how do omega 1 and omega 2 and omega 3 change with time? That's what we're going to get to. We've got this differential equation over here. So if we just plug in everything, I'm not going to plug in the full way of writing it in terms of components. If we plug in what we have, this becomes, we've got a derivative with respect to the B frame of this 3x3 matrix written in the B frame times omega written in the B frame plus omega cross, and now we substitute in again I C times omega, and then this equals LC. And we could also write that in the body fixed frame. So this is an equation where everything is written in B frame components. This is a vector equation, all in B frame components, whatever that body fixed frame is. And remember, the body fixed frame could be moving around with respect to an inertial frame. And that's what makes this seem kind of crazy, but it's okay. It's all right. We have a derivative here. Let's deal with the derivative. A derivative of a matrix times a vector. We could use the product rule for that. It is a derivative of this matrix times the vector plus the matrix times the derivative of the vector, then plus omega cross. I'm just repeating everything from up there. This doesn't change, except it's all written in B-frame components. This is why we write the moment of inertia matrix in the body fixed frame, because everything's constant. So this thing here, you take the derivative of things that are all constant, they're not changing, right? Because this is constant. That matrix is constant. All of its entries are constant. You've calculated it once and for all. That's the mass distribution with respect to the body fixed frame. So this is 0. So it falls out, goes away. The mass distribution doesn't change. We're assuming a rigid body. If we assume something where there are moving parts, then okay, we would have to adjust that. But for now, we are not. So that part goes away. And then we're left with just this. This is equivalent to equation 4.34 in the book, although I'm being more careful about what frame things are being written in. So if we were to write this out, these derivatives of the omega vector, individually, that's just going to be omega 1 dot, omega 2 dot, omega 3 dot. It's just the time rate of change of those. So this will all become, all right, it is this way, IC times omega 1 dot, omega 2 dot, omega 3 dot. It's just the rates of change of those body fixed frame components. Plus, you could write this in different ways if you want. You could write it as omega 1, omega 2, omega 3 cross this matrix. You notice there's lots of omega 1s, omega 2s, and omega 3s flying around. And then we'll write the moment. I'll just write it in terms of components, say L1, L2, L3. Those are the three components of the moment in the body fixed frame. And you could take this further and write it in different ways. So if you write this out, it'll look like some horrendous thing if you use just any old frame. So this is another version of Euler's rotational equations of motion. You might say, is there a difference between Euler's equation and Euler's rotational equation of motion? No, it's just a different way of writing it. So for whatever reason, yeah, the book will call this 4.35. Things simplify, and this is why I wanted you to know what a principal axis frame was and how to find it. If you write this in a principal axis frame, so if we choose as our body fixed frame a principal axis frame, then the advantage that gives us is that this moment of inertia matrix is just diagonal. We lose all those off diagonal elements. And when I do that, instead of writing it as I11, I'll just call it I1, I2, I3. So that's it. When we've chosen a principal axis frame, when you do that, then this Euler's rotational equation of motion simplifies to a point where it's kind of easy to work with. It becomes I1 omega 1 dot minus I2 minus I3 omega 2 omega 3 equals L1. I might say plus cyclic permutations, which just means all the indices just sort of move back. So this becomes I2 omega 2 dot. So we've just sort of said, okay, now you go here, you go here, you go here. Well, and then this goes back over to there. That's kind of ugly looking. So I'm going to get rid of that. All right, so then this is, if this was I2 and everything moved back, so then this is I3, and this becomes I1. And this is L2. Everybody move over one again. I3 omega 3 dot minus I1 minus I2 omega 1 omega 2 equals L3. Sometimes these are called Euler's rotational equation of motion. It's the same thing. It's just written in a nicer format. That's kind of pretty. This is just writing it in a principal axis frame. So this would be the same thing. Euler's rotational equation of motion in principal axis frame. Okay. This is nice. What does this tell us? These are three nonlinear ODEs for how the body fixed angular velocity components change. So you could think of it as, if I were to draw not something arbitrary, maybe something more engineered, then there's our center of mass, and we have an angular velocity written in the body fixed frame, and it's going to have these three components, omega 1, omega 2, omega 3. They'll be changing in time, right, with respect to our, if this is a box, then if we choose our frames to be B1, B2, and B3 to be normal to the different faces of the box, like this. Choose this. This is a principal axis frame for this box shape. Then this equation, it's the most simplified version of Euler's rotational equation of motion, describes how those components change, right? It's just three ODEs. The I's are all constant. I1, I2, and I3 are constant. Now, the moment might be changing. It might be changing with time and also position. I don't know. The moment could be due to thrusters on board a spacecraft, or due to some flywheel, some momentum wheel that is being used to redirect how this is orienting. Or it might be due to something else. Maybe it's due to drag that's heavier on one side versus the other and making this thing turn. So you'd have to compensate for that. But this is the most simplified thing. So that from this, we would get, if you solve it or used In general, you will do this computationally. We will look at an analytical case just to get some insight. But if you were to solve this, you would solve it numerically, and this would give you omega 1, omega 2, and omega 3 as a function of time. So you'd start with some initial condition of what's omega initially, and then you could solve it. You solve that numerically, then from rigid body kinematics, you can find how the B frame is rotating with respect to some inertial frame as a function of time. So if you want, that could be given by some set of Euler angles. Or the other thing we talked about, the Euler parameters or quaternions, however you want to parameterize it. But that's sort of how the pieces fit together. Now, the simplest case that we would look at is when there's no moment. In general, out in space, there's no moment. And the weird thing about rigid body dynamics is that you can get some interesting looking dynamics when there's no applied moment. No applied moment means that L1, L2, L3 equals 0. And that's called the free rigid body. So that's a special case, free rigid body. It just means it's free of moments, or sometimes we say torque or moment free. It just means that L1, L2, L3 are all equal to 0. So the right-hand side up here is equal to 0. And I guess I could bother to rewrite it. We set those equal to 0, and I'll put this stuff on the right-hand side. Then you could see, okay, I1 omega 1 dot equals minus I2 omega 2 omega 3 I2 omega 2 dot equals minus I1 minus I3 omega 3 omega 1. And the last one is I3 omega 3 dot equals minus I2 minus I1 omega 1 omega 2. They're purely nonlinear because the right-hand side, and they're coupled, but it can be solved. This is a nonlinear ODE that can be solved. Maybe you're not thinking of it as a single ODE. It's 3 coupled ODEs that can be solved given initial conditions. Well, or so we think, seems like that would work. So at some initial time, right, this vector is, let's call it omega 1, 0, omega 2, 0, omega 3, 0. It can show some interesting dynamics. Typically, what we want to do first is look at special cases. So say, what's a special case? If you stare at these ODEs, a special case would be if 2 of the moments of inertia are equal. So these are further special cases. And 2 of the moments, these are principal moments, are equal. Because if 2 of them are equal, then one of these coefficients is going to be 0. So it's commonly taken that I1 is equal to I2, and then we let I3 be the one that's different. So for example, if I1 is equal to I2, this case, and it's the same thing if I3 is equal to I1 or whatever. It's just for ease of explanation, it's typically taken that I1 is equal to I2. This case of 2 equal principal moments of inertia is called a symmetric rigid body. Sometimes it's called axisymmetric, but I think this can be deceiving because, yes, it's true for if you have a cylinder, like a perfect cylinder, then yes, this is an axisymmetric body, and the moment about B1 and about B2 are equal. Maybe we'd call those the transverse moments. They're equal to each other. And then I3 is not equal to that value. If it was, then we'd have something that's completely symmetric. These are called symmetric bodies, but it doesn't have to be a cylinder. You could have a rectangle that has a square cross section. So a rectangular block with a square cross section. It's not axisymmetric, but it also has I1 equal to I2, right? If we were to write this is B1, this is B2, and then this third one is B3, these moments are also equal. I1 equals I2, like this. And then these have kind of 2 different cases, and we'll just have to work on it next time. One of them is we've got the I3 does not equal IT. If I3 is the largest moment of inertia, so if it's bigger than IT, that means you have sort of a squished thing, kind of like what I drew here. I think this probably also qualifies, this big piece of lead on my coaster. So it has a lot of mass that's perpendicular to that axis, and that is called an oblate shape, that squished. If I3 is less than IT, then we call this prolate. If you want, it's tall, skinny. So this is an example just from how I drew it and what this is. This is prolate. So the moment of inertia about that direction is the smallest, and you'll get different behavior. And just to give you a preview with some videos, here is an oblate body out in space. It's hard to see, but right, the angular momentum vector is at h, and it's not changing. It's purple here. Angular velocity is a blue thing that's incredibly hard to see. But you get this idea of, in general, this thing is going to be looking like it's tumbling. It's not tumbling erratically. In fact, this motion is called precession. So that is one type. And then here's the kind of tall, skinny thing, prolate. And it moves, seems to be moving differently. And we will understand all that stuff later. All right, so that's all I had for today. And so if I put this 1/3 of the way up, I can balance it. Wow, that's cool. Should make your own triangular plate.